continue straight from previous video where we have calculated the design wind speed for 4 orthogonal directions. Now the next steps, we need to check that everywhere design wind speed is greater than 30 meter per second. So if you're checking 33.8, which is greater than 30, 34.7, which is greater than 30, 40 meter per second, which is greater than 30, and 41.4 meter per second, which is greater than 30. So that's notes is given here in Australian standard on page number 8. On page number 8, AS NZS 1170.2. On page number 8, they have written here for ultimate limit state design width should not be less than 30 meter per second. So we check that value, which is V design speed is greater than 30 megapascals. Close 2.3 on page number 8. They have one sentence written that we should check whether the design speed is greater than 30 mega. If it is less, then we just take 30 meter per second. Now next we like to calculate design wind pressures. Now the equation for design wind pressure is P equal to 0.5 times the density of air, design wind speed square times aerodynamic design factors and dynamic response factors. Now this equation is given in close 2.4.1 on page number 11. So if I show it here on page number 11 on the close 2.4.1, it has given equation design wind pressures P equal to 0.5 density of air times design wind speed square times aerodynamic shape factors times dynamic response factors. Now we have given density of the air, which is 1.2 kg per meter cube, and please note these equations gives the answer in pascals, which is Newton per meter square. Now density of air is given 1.2 kg per meter cube, so we're going to substitute density of air 1.2 kg per meter cube. So in these equations, if I substitute density 1.2, I can get 0.6 design wind speed square times aerodynamic shape factors times dynamic response factors. So that is in the answer in pascals, because in Australian standard it says that the pressure given in the pascals. So that is pascals here, and 0.6 divided by 1000 to convert pascal into kilopascals, and all other parameters are written same. That is given 0.0006 V design square C, these two parameters. Now dynamic response factor is given taken 1 here, because we are not considering dynamic response here for these buildings. The information is given in the section 1 on page number 41. On page number 41, there is the information given about dynamic response factor in Australian standard. So we substitute dynamic response factor 1 here. So 0.0006 design wind speed square times CFIG times 1. So that's give us 0.0006 V design theta square times C. So that give us 0.0006 V design square times C fix. Now once you get these equations, which is this in that form, we can substitute design wind speed. We have 4 design wind speed. Now we have obtained this one in the previous video. If I can show it here, it's just we find those 4 velocity. I just put 40 as a rounding here. That is 40. That's the only difference. All other values are same. Now in that case, we have equations that we just obtain in here, which is 0.0006 V design square C fix. Now in this case, we can substitute the design wind speed. For example, theta equal to 0, we have 33.8. So 0.0006 times 33.8 square times the aerodynamic shape factors. So the answer is given 0.69 aerodynamic shape factor. So now we can have a 0.69 times aerodynamic shape factor for theta equal to 0. So we get theta equal to 0 by substituting this 33.80. Now for the second case, we can obtain for 90 degree, where we have 34.5. So if I substitute 34.5 square in this equation, I should obtain 0.71 times aerodynamic shape factors. Similarly, for theta equal to 180 in these equations, we can substitute 40 squares times 0.0006 give us 0.96 times aerodynamic safe factors. And similarly, the last one, which is the 41.4, so substitute 41.4 square here times 0.0006 times the aerodynamic safe factors give us 1.03 times aerodynamic safe factors. So stop here to calculate the design wind pressures, and in the next video I taking the further steps for solving this example. Thank you.